So this may be boring if you're going to go fast, but go ahead. We'll show the basics of how FPGAs work and give the amount of memory you need in neural network systems, the embedded memory. But the embedded memory is an important aspect of the overall characteristics of the FPGA. Then we'll look at a couple of results on optimizing neural network architectures for FPGA implementation. Okay. So sort of the classic FPGA is classic FPGA is a bunch of logic elements with programmable logic elements, programmable interconnect, and then programmable I/O. Right? Modern FPGAs, the bigger ones tend to be heterogeneous. They have a lot of different types of elements, so we'll get to that in a few minutes. But this is your classic FPGA right here. Question: is this a computer? No. Why? Right. So the von Neumann model of a computer says what? So we have a central processing unit and a separate memory which stores instructions. Right? Okay. The idea is you fetch an instruction from the memory. Central processing unit then does what the instruction tells it to do. Okay? There's no fetching of instructions here, right? Even though there may be, there are a couple of ways to build these things, but a lot of them use SRAM to store values in here, but you're not fetching them, right? That memory directly controls the output down. Okay, so this is not a computer. This is not a von Neumann machine. You can use it to build a von Neumann machine, but an FPGA is not a von Neumann machine. Okay. So, you see somewhat different terminology floating around. Combinational logic block is CLB. A logic element, basically the same thing, but people use different terminology. The lookup table is one way to build a combinational logic element. And then an I/O block includes both the connection, the physical connection, along with associated electronics for driving and sensing and so on. So the logic element in an FPGA is programmable. You can configure it in order to do different functions. Okay? So using an FPGA means setting up a configuration that has different logic elements doing different things. And of course, not all the logic elements have to do the same thing. So this is gives you even more control over the computation than does something like a CPU. Typically, logic element includes a logic block that can do arbitrary functions, plus some kind of register, and most of them contain some specialized logic as well for things like addition. And because doing arithmetic entirely with these generic logic blocks is usually too expensive. And so this relates very closely to neural networks because we're going to do a lot of arithmetic. So we have to understand what specialized arithmetic blocks we have. So a lot of FPGAs use static RAM to build a logic element. That means basically you use the SRAM as a lookup table. Okay? Why is a lookup table a good model for an FPGA, for a logic element? How do we specify a Boolean logic function? One way to do it. Table. right? So the table you see in your undergraduate textbook on logic design translates very nicely into an SRAM. Okay? So one interesting property of that is that all the different logic functions you can fit into this SRAM have the same delay, have the same area. So logic design has some different trade-offs. It also means that you're going to burn power even when you're not using it, right? Because you have to keep the SRAM powered up. A register connected to the output of the lookup table is usually pretty cheap. So that's a very common element in these logic elements. So generally you have a configuration bit that decides whether you're going to use that register or not. If you're not going to use it, you connect the output to the lookup table directly. If you are going to use it, you select that input to the multiplier. Okay, so here's our lookup table. Right? We have this is a 2-input function, so we have 4 rows in the lookup table. Oops, get clever in this, but you can have different functions in this lookup table by putting different values in the output column, which corresponds to storing different values in those locations in the SRAM. And so all we have to do to change what the logic element does is to determine what values we want to put in this table. Okay. So from a logic design point of view, the problem is to break up a big function into pieces that are of the size of our logic element. So, for instance, a 4-input function is fairly common, right? Once we get below 4 inputs, it doesn't matter, right? Because it always fits. But if we have a function that's bigger than 4 inputs, we need to break it into pieces, such that each of the pieces has 4 inputs. Okay? And there are different ways of breaking up the function may require different numbers of blocks, or they may have different depth in the logic. Okay? So there are, in fact, some solutions that are better than others. The physical element, once again, once we get within a block size, it's solved, but basically we have to figure out how to place the logic elements and how to route the connections between them in order to implement the functions we need between the blocks. Okay? So when we're doing logic synthesis, on the one hand, we may use common subfunctions to reduce area. That's going to introduce extra connections that we have to take into account. Okay, but the common subfunctions may give us some net benefit. We can also rearrange things to reduce the depth of the combinational network to reduce its delay. Once again, let's look at the delay of a given block is always the same, but if we have more blocks in series, we're going to increase the delay of the bigger function. So we've broken our logic into lookup table sized pieces, and we need to place them on the FPGA. If routing were free, it wouldn't matter where we place them, but we have a limited number of routing resources, and so we have to evaluate the placement based upon the available routing resources. We have to make sure that we can fit the connections into the available set of connections, and we also want to make sure that we don't have wires that are too long. So we have a critical function, the function whose timing determines the overall system timing. Putting logic elements at opposite ends of the FPGA may not be a good idea. So how does this wiring work? Well, we've got two things going on, two types of programmability. So basically, we're going to use registers to program switches inside the interconnection network, right? So in this case, we have 4 routing channels here. There are, and there's a set of connections in between these different routing channels. We can use registers to enable, say, a certain connection between this channel and that channel. Okay? We also need to configure connections within the routing channel. So this is an example of a global routing path. We want to connect this logic element at the bottom left to this logic element in the upper right. So we're going to go along, go out to the vertical channel here, go to this horizontal channel, take another vertical path, another horizontal path, and then you get the vertical channel for the final connection to this logic element. Within each of these channels, there are several different wires we can use. We need to make those connections. We'll see, even within a channel, we may hop around between different wires. We need to solve the global routing problem. We need to solve the local routing problem. And they do interact to some extent. Now, the good news for neural networks is that the connections tend to be more local. So the global routing problem is a little easier to solve. Let's zoom in a little bit. Each routing channel is going to have several tracks of wiring. Okay? So here we have 2 choices in this case. Let's assume that each track goes along the entire length of this channel. We can still choose between using the upper track or the lower track in this case. In the vertical channel, we once again have 2 choices between the left and the right vertical track. Once we've made those 2 choices, that tells us how we have to program this switch box in the middle here. Right, so for instance, if we're connecting the upper wire here and to the right wire here, we would need to program this connection in order to connect those 2, the vertical and horizontal wires. So we can measure the quality of a given routing result based on how many wires we're using in each channel. We can also look at the length of wires, which is associated with the delay of the wire. So, generally speaking, as long as it fits inside the channel capacity, we're okay. The channel capacity is determined by the FPGA, right? We don't get to design our own FPGA. We're told this channel has this many wires. Delay is a design parameter for our designs. So in fact, those channels are broken into pieces, and so it's a segmented wiring problem. Okay? So one of the design parameters for the FPGA is how long those segments are. So on the upper wire, we put a programmable interconnection point at distance 1, right? So each of these is an input or an output to a logic element, and we put a connection point at every one of those. This means that we have more options on how to connect. It also means that there's a little more delay in this wire because each of these connection points slows down the wire. The bottom wire has a segment length of 2, right? So we're only connecting up to every other vertical connection. That means that, for instance, this vertical connection can't connect to this wire here, which may limit some of our placement options. But it also means that this wire is going to be a little faster. Okay? So, you know, I/O is perhaps not the biggest concern in the neural network, but we do have to worry about the interface to our global memory. Generally speaking, we can configure the I/Os as inputs or outputs or bidirectional. And most FPGAs give us a bunch of combinations, including different, whether they have registers or not, the voltage levels we can use, the slew rates on the output, and various others, I/O standards that we can use. So, so we need to configure the logic elements, we need to configure the interconnect, we need to configure the I/O. Okay? We mentioned that a lot of these are done with SRAM, which is reprogrammable. Some FPGA technologies use NKFuse, which is programmed once, but has advantage for radiation hardness and other reliability issues. Some use Flash, which is reprogrammable, sort of in between SRAM and NKFuse in its characteristics. Configuration is typically done offline, although there are some FPGAs in which you can reconfigure some of the parts of the FPGA while it's running. I don't know of anybody who's using that for neural networks right now, although could have some interesting applications. We talked about the difference between CPUs and FPGAs. Okay. So that's a classic FPGA, but most big FPGAs today are in fact systems on chips. Okay? They include not just an FPGA fabric, they often include one or more CPUs, which may be fairly powerful CPUs. They include a lot of embedded memory, and they may have very specialized I/O functions. Things like networks and memory and so forth. This table gives you characteristics of a couple of different high-end FPGAs, just so you can get a feel for what they include. So here's two Xilinx FPGAs, two different technology nodes, 20/16. And then compare that to an Altera designed for the 14-nanometer node. Large number of logic blocks, 5 million, right? Well, the middle one is 3.7 million, but you know, several million logic blocks, large amounts of block memory. Okay, so this is onboard, fairly parallel memory. We see 88.6 megabits on the 20 nanometer Xilinx part, 94.5 on the 16 nanometer Xilinx part, and 137 on the Altera part. Okay, that's a lot of memory. Multipliers, see a wide range of number of multipliers from a low of 2880 to almost 12,000. Wide variation in the number of I/O pins, and you see that since networking is a big application for a lot of FPGAs, a lot of them have support for serial I/O, which can run very, very slow. Yes.
Right. How many? Is that 18
I forgot to write that down, but I believe, yes, that for these two, these are like 18 bits or 16 bits, something like that. You'll notice here that in this case, in the Altera part, you basically have half. If you go to a larger multiplier, you basically have half the number of multipliers. But once again, doing a multiplier entirely with lookup tables would be very expensive, right? So these SOC designs have been optimized for DSP kinds of applications because they use some of the transistors in the logic element to do multiplication. Okay. So let's think about the memory for a minute. So this is a very different type of memory than what you see in a processor or even in a GPU. Okay. So in the case of the exact numbers are going to vary from FPGA to FPGA, but in the Xilinx Ultra scale, the memories are 36 kilobits in size, and each has dual ports. Okay, so we've got, if you've got 90 megabits of memory with 18 kilobits per block, that means you've got thousands of blocks that you can access in parallel. Okay? So this is even more parallel than a GPU as far as its memory architecture goes. Okay? The synchronous interface are relatively simple to design. You can configure them for the port width for reading and writing. You can also cascade the memories so that you can take the output of one memory and use it to feed and address it in the next memory to do more complicated operations. Okay? But this is an important point for neural networks. Lots of very small memories. Okay. Once again, if your operation is just a little bit bigger than this block, you got a problem. Right? So you have to make sure that you design your algorithm so that it fits in these blocks, but you have a lot of blocks that can all run in parallel. Okay? Okay, so let's start to think about optimizations for neural networks that are specific to FPGAs. We can think about making use of this memory. We can think about pipelining because we have we're doing our own logic design. We can pipeline it any way we want. We can think a little bit about the interconnect, and we can also think a little bit about off-chip communication. Okay, so Microsoft published a paper in 2015 on their FPGA design to implement the AlexNet architecture. So remember, AlexNet was originally targeted to use GPUs, right? So they tweaked certain parameters to make it fit on this dual GPU platform. In this case, they're not modifying the neural network, they're taking it as it is, but they're implementing it in an FPGA. If you were starting from scratch, you might want to redesign your FPGA, redesign your neural network for the different, advantages and disadvantages of FPGA. But in order to do that, you would probably need to go back up to Cafe or something like that, experiment with the neural network topology, figure out what connections make sense and so forth, and then translate it down into FPGAs. These guys were just seeing how much better they could do with an FPGA. Okay? So they're concentrating on evaluation, not so much on training. Okay? They use an Altera FPGA, in particular this Catapult card, which has one of the big Altera FPGAs on it. And this is attached to a Xeon processor. So these figures are from the Microsoft paper. So because they're concentrating on the forward propagation, they're basically, you know, convolution is a big part of what they're doing. They have to do the nonlinear operations also, but they have to do the convolution, right? So they have these boxes within the larger window of a given depth. They're going to do convolution on those, and then the pooling operation is going to take a given convolutional output and subsample it into a smaller space. Okay. The architecture they came up with looks something like this on the right-hand side, and it's basically designed to do to work on one layer at a time. Okay. So. Here is the set of inputs. On the left side, on the right side is the set of weights you're using. Here's the set of processing elements that are doing the operation of the convolution or the pooling or whatever. The network on chip down here makes sure that the results for the P array go back up into the buffer in the right order. Okay? At different points in the AlexNet architecture, we saw that you're looking at different size convolution windows, right, and perhaps different amounts of subsampling, right? So there's not just a single pattern of memory addresses you're operating on. That's why they have this network on chip, and that's why they have this controller up here. Right? So you're basically doing convolution, you know, with, of course, doing the nonlinearities and other things in the middle. But the parameters change somewhat from layer to layer. Okay? And since you can't fit all of these convolutions into a single FPGA, you're also windowing across this larger block in order to do all the convolutions you need to do. So you have to do that level of address generation also. Right? But this 2015 size of FPGAs allowed you to basically do one layer processor per FPGA. So then you iterate that over all the layers to do the entire CNN. Okay? Now, the next generation of FPGAs, which came out in the past year or two, is big enough that you're closer, at least, to being able to do that entire network on a single FPGA. Okay? So, as we move from technology generation to generation, the trade-offs change very quickly. Right? We're right at the knee of the technology curve where this whole neural network thing makes sense. Right? So the trade-offs are changing very quickly. Okay? You know, in the GPU space, the programming of for the new generation of GPUs that's just coming out from the last generation has changed. It's changed even more quickly in the case of FPGAs, and it changes very quickly, as we'll see in the case of ASICs also. Well, let's see, what do they get out of this? So these are various benchmarks. These are in different implementations. So the bottom row here is a Tesla K40, and these are some different FPGA combinations. Okay, so the Tesla, and I believe this is on the ImageNet set of benchmarks, was running at 235 watts. And 500 to 800 images per second. So they quoted the best prior FPGA as being, you know, slower than that and no power numbers. Their FPGA was somewhat slower, but it's burning about 1/10 of the power. Okay? Now, keep in mind, you say 25 watts, who cares about 25 watts? But remember that plot we showed before lunch on the number of processors it takes to do training, right? Now this architecture is designed not so much for training, but you would expect, you know, significant benefits for the power consumption of training also, right? So, you know, if you're talking about taking 100 servers running for a half a day and reducing their power consumption by an order of magnitude, that's a big reduction in power consumption, right? So the reason Microsoft was interested in FPGAs was because of power consumption. Okay? Okay. Jason Kong's group at UCLA also has done a lot of work on FPGAs for neural networks. So in their 2015 paper, they talked about using loop theory, you know, the kinds of optimizations we do in parallel programming in order to optimize the FPGA design. And analyze the design space, they use what's called a rooftop model, right? So this is the x-axis is sort of the quantity of computation or communications, and the y-axis is performance. And you notice that this has the performance is limited by different things in different parts of the graph, right? So for small amounts of compute power you have, performance is limited by I/O. Okay. But once you get up to larger computational units, then basically performance is limited by the amount of compute. Okay. So they ended up with an architecture that, you know, at a very high level looks similar to what they were doing at Microsoft, in that they're doing one layer of the neural network at a time, right? So they have input buffers and output buffers. These are double buffered, right, for parallelism. A set of compute engines. They have a interconnection network. They use a crossbar in particular in order to allow them to route data in the proper way, and they use 32-bit floating point units. Okay? They got to 18.6 watts, and that's with 61 gigaflops performance. So they did very well on the power consumption also. So they spent a lot of time taking the GPU code and performing loop optimizations in order to get the most out of that layer architecture. Okay. So different layers of the neural network are going to have somewhat different optimizations. Right, so their goal was to understand the way to optimize each layer, and then to design this engine that supported those optimizations for the different layers. Okay, so how many of you have optimized loops in parallel in the program? Okay, so you know we don't have time to go through all the theory of loop optimization. It's a very old field, but let's start off by looking at the design specs. Okay, so here is a loop which you're saying, you know, this is a very simple loop. It says CI is equal to AI plus PI. What are the constraints on what you can do in parallel? So how many operations, if you wanted to do more than one loop iteration at a time, how many loop iterations could you do in parallel? n, right? Because they're all independent, right? Now look at the right-hand loop where C of I is A of I plus C of I minus 1. Okay? So now C of I depends upon the value of the previous loop's computation, right? That's called the loop carry dependency, and that's an example that limits the amount of parallelism you have. Okay? So we want to look at data dependencies not only within the loop iteration, right? This is generally going to have more than one statement here, but you also need to look at dependencies from one loop iteration to the next. Okay? We also talk about perfect and imperfect loop nests. So a perfect loop nest has no control. Okay? A nest is a set of loops, one inside the other. Right? So this is 3 loops, one inside the other. But this is a perfect loop nest because there's no if statement. This is an imperfect loop nest because we have a conditional in the middle there. Okay, so not all of the iterations in the innermost loop are going to be executed. Oops, excuse me. Given that, there's a lot of things you can do. Loop permutation changes the order of the loops inside a loop nest. Index rewriting basically changes the loop iteration variables. Loop unrolling copies a loop body. Loop splitting splits one loop into 2 loops. Loop merging takes 2 loops, one after the other, and combines them. Loop padding adds data elements to change how we walk through memory. So let me give you some examples, a couple of examples here. Here's a loop nest. Okay. So here, this is basically a matrix times a vector. Multiplication here. So in the original loop nest, J is the outer loop, I is the inner loop. In this case, we have swapped the 2. So now I is the outer loop, J is the inner loop. Did that change the result? In this case, no, because we have a simple loop body in the iteration, right? In some other cases, it could, right? Like if we had a loop carry dependency, if you change the order of loops, you're probably messing something up. Okay. Here are 2 loops doing X and Y. We can fuse these together fairly easily because these are very independent, right? So now we have, oh, excuse me. Well, yeah, it's not, yeah, ignore this. This is actually not a good way to use it, right? We can combine these 2 into a single loop. If we have a loop body with these 2 things, we can also split it into 2 loops, right? So if you merge 2 loop bodies, you're going to need more variables inside the loop body, right? But you're also going to have less loop overhead. You may also be able to reuse some fetches. In this case, both those loops access a sub I. Okay? So we have this library of set of operations we can do to change the structure of our arrays. The polytope model is a theory that helps us understand how to do that. And once again, we don't have all the time to go into all the details. But the basic idea is that we can represent the data dependencies as a matrix, right? So we have two loops here, I and j. If those are dimensions in a space, we can draw out the data dependencies for this loop look like this. So in this case, C of ij plus 1 depends on C of ij. Right? So this value here depends upon that value. Right? The dependencies only depend on j. Right? So they go in this direction. I may have messed that up. I may need to reverse this. But there are no dependencies in the other direction. If we have a different code inside the middle of the loop nest, we could have data dependencies going vertically, we could have data dependencies going diagonally, all sorts of different directions. Right? We can describe that as a matrix like this, where n is the size, and so this loop goes from 1 to n. This loop goes from 0 to n. The inner loop goes from 0 to I. That's what this describes. And now by using matrix algebra, we can rewrite the loop in a way that we project these data dependencies in a different way. That means that we're walking through memory in a different way. Okay? So the matrix algebra allows us to express different ways to map these data dependencies onto memory. Okay? And given we know we have a certain memory structure, we can then go from the easy way to write this loop into a way that maps well onto the memory we have. Okay? That makes sense, right? So if you were, if programmers has to do everything by hand, right, they would have to look at the memory and say, remember when we talked about the GPUs, we said, okay, we want to do 2 columns at a time, yada, 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 right? Okay. But that means that the programmer has to understand, right, how the memory works and everything, right? You want the programmer to write the loops in a way that's natural, a way that's easy to see that it works. Okay? But then you want to reorder the way you do the operations so that it fits well onto the memory structure. Okay, so you want to, how should I put it? Can you do these 2 operations in parallel? No. Can you do these 2 operations in parallel? Yes. Yes. Right? So you want to walk through the data. If you want to maximize parallelism, you want to walk through the data this way. Right? Rather than walking through the data this way. Okay? Yeah. This is our original code. This is the data dependencies in this code. Yeah, now that I look at it, I think these are swapped. I think these 2 should be swapped. This is J, this is I, right? But this is the set of data dependencies. So this is all the data dependencies for all the iterations. Okay? This looks like an upper triangle because that's the way the loops work, right? It's only doing the upper triangular part of the operation, okay? We can describe, right, but these are not just random data dependencies, right? This has a structure. So this matrix describes the order in which we walk through the data, okay? So now we can change the order in which we walk through the data by matrix operations. Okay, so we do a bunch of matrix operations, and then we reverse engineer the loops from that. And that says now we have something that computes the same thing, but in a different order. Make sense? A little more sense? This is a big topic. We're just brushing the surface, but you know, this theory was originally developed for software, really, for caches, but these guys and other people have used it for optimizing the hardware design. Okay, so you need to know, in the case of the FPGA, right, you have to read out values from the input buffer in a certain order, right? And if you use the right order, you can keep more of the processing elements busy. If you read them out in the wrong order, fewer processing elements will be in use. There'll be more I/O, right? So they use this theory to maximize the parallelism of the convolution. Okay? Okay. So caffeine was, I'm pretty sure, developed by the UCLA guys. It takes the cafe library that we saw before, that's really oriented towards CPUs and GPUs, allows you to map your code onto an FPGA model. And it has a simple optimization routine that goes with it that'll to optimize the mapping onto the FPGAs. And they did one example where they got up to 636 KOPS on a Cortex 7. People have also looked at how to do various operations in hardware, and this paper proposed using stochastic rounding, which is something you can do in an FPGA fairly easily. Right? So this idea has two parts. First, the idea of using stochastic rounding, and secondly, how you build a hardware unit, an FPGA hardware unit, to do that. Stochastic rounding says, there's some probability that you're going to round down and some probability that you're going to round up. Okay? The probability depends on how close you are, right, to the midpoint. Right? If you're 1.001, you're not likely to round up by spots. Right? If you're 1.999, you're not very likely to round down. If you're right in the middle, it could go either way. So numerically, they showed that stochastic rounding was nearly identical to a 32-bit floating point. And then they showed a sort of interesting hardware architecture to do this. So this is a systolic multiplier. Systolic means that basically the values move in wavefronts, okay, or beats. Okay? Systolic architectures are very pipelinable, so you can get very high throughput for this, which is the reason for doing this. Right? So they're saying we want a systolic multiplier because it's very pipelinable, very high throughput, and stochastic rounding is easy, relatively easy. It's a lot easier to do with a systolic multiplier than would be regular floating point. Okay? So basically, they have a two-dimensional array of small multipliers for the data. moves through from left to right, and then they have units up at the top of each column that control the rounding. Okay, so it's not, well, the paper was fairly short. I'm not sure I understood all the details of how this thing worked based on what they said in the paper. This is an interesting, we talked before about the numerical accuracy versus the accuracy of the neural network operation. This relates numerical accuracy to the operation and down to the hardware architecture of the numerical computation. Once again, there are several other papers out there that go on this general topic of efficient hardware implementations that give good enough results for neural networks. This is one example.
How many bits?
Right. I don't remember exactly. I believe it was. I don't remember exactly. I think it was 16 or 32 bits. So I don't remember exactly, but it's fairly long precision, right? But floating point has this sort of sequential bottleneck, right? Because you have to denormalize and then renormalize. Basically, this stochastic rounding gets rid of that. Oops. And so this was this takes a fair number of multipliers in the hardware unit, but overall, because it's pipelinable, it's fairly efficient. The other thing that they didn't really talk about in this paper is, given that you've got this two-dimensional array of multiplier units, how does that relate back to this block diagram? Right, and I don't know the answer to that exactly, right? So this block diagram sort of makes it look like the PDs are fairly small, relative to the memories and so forth, right? But when you've got this big pipeline multiplier, a wavefront multiplier, this block diagram becomes more complicated, right? Because now, you don't just have this block diagram assumes that all the multipliers are sequential, basically. Right? With the wavefront multiplier, you've got a lot of values in flight. So I don't know if those guys looked at how to integrate that design into the overall accelerator architecture. But it's an interesting idea. And it's right at the heart of the architectural trade-offs that you need to make these systems work. That is pretty much what I had to say for this part of the session. Does anybody have any other questions? Let me point out that this last paper about the stochastic round-off is in arXiv, right, which is this sort of open publication kind of thing. There are actually a fair number of results in this field that are in arXiv that haven't been published in conferences or journals. This field is moving so fast, right, that these results come out very quickly. So in this case, arXiv is actually a pretty interesting place for some of these results. Now, of course, this stuff hasn't been reviewed at all, right? But you can look at the number of people who've cited a given paper to get some idea of whether it's useful. Okay. Any other questions? Yeah.
How do you compare GPU with each network? watt do you think was the output?
Oh, well, then that's, right. There's the answer right there, right? So, for 1/3 the performance, they use 1/10 the power. So it's about 3x more efficient, roughly speaking.
Are they based on the same?
Well, I don't know. But it doesn't matter, right? Because you're not designing either one of them. Right? You're not going to design your own GPU. You're not going to design your own FPGA. Right? So at the time, the Tesla K40 was not the fastest GPU to get out there, but it was pretty good. Right? This was a very high-end FPGA for the time. Right? So they were, they're doing significantly more energy efficient than the GPU. And ASICs, you would expect to be even more energy. And given the number of neural networks you need in a data center to do, big volumes of this, that, 3x power reduction is very, very significant. Now,
at the beginning, FPGA does not have ESP.
Right. Oh, interesting. So yeah, up the level and do matrix operations and so forth. They might. Yeah. And are there sort of hybrid architectures that are in between an FPGA, and a full hardcore ASIC, right? It was just doing a particular neural network structure. There probably are. I don't know whether, Xilinx is doing this. Altera now is controlled by Intel, right? I think I've read something about they're very interested in neural networks because they know a lot of data centers and stuff, but I can't remember any specifics. So my guess is we're going to see FPGAs with some more features. How aggressively they go with those features, I don't know. But I think really what you're asking is there this new category of chip? And the answer is almost certainly yes. The question is, what does that look like and who's going to get red shot to do it? Anything else? Okay, so you want to start at 3? Does that sound reasonable?
Yeah.
Okay.
我想我们还是休息30分钟啊，因为这个沃教授有时差哈，所以我们3点开始，然后让他早一点休息。Okay, so we take a break with a coffee and come to dinner.